Good. So then, good morning. Let's start again on the foundations of Bayesian inference. I want to, before we go into continuing our explorations there, which today will focus on conjugate inference and numerical inference, and then tomorrow on variational inference, briefly highlight again what we really learned yesterday, so the meat of it, so not all the intro stuff, but what we've seen. So again, always keep in mind that the probabilities that you see here, specifically when it comes to the prior and to the posterior, are quantifications of uncertainty. There's not an idea of sampling something or that these things exist in the world. It's just you are asked, how certain are you? You say, well, I'm 50% certain that the parameter is larger than 0. And that's what these probabilities describe, this uncertainty. Problem is a little bit the likelihood, and maybe we can discuss later what that really should mean, because for the likelihood, it's much easier to think in terms of a sampling approach. But of course, the more interesting things in Bayesian inference are prior and posterior, and they are quantifications of uncertainty. The crucial can you turn your mics off at home? The crucial mathematical model in this whole business of Bayesian inference is this joint distribution over something that can be observed and usually models data, and something that can only observed by means of the data, which is then also called a latent variable, or not directly observable variable, or unobservable variable. The crucial entity is this joint. Guys, can you turn off your mics at home, please? And that's what we introduced. So we have this joint distribution over data and parameters. And I changed here a little bit yesterday in the afternoon, the notation, so that it really makes sense, so that we distinguish between the random entities, which now have this epsilon, which looks like a V, and this var theta, which are the random entities, random variables, random vectors, random functions, whatever, and the values that they take, which are the y's and the thetas, because we have everything formulated in terms of PDFs and PMFs, and then it's about the values that these things take. It's a minor thing, but it's better. So that's what we introduced. So the joint distribution, we also said the posterior distribution is interesting and important, and the posterior distribution can just be derived by means of Bayes' theorem, which is just a way to write conditional probabilities. There's nothing Bayesian about Bayes' theorem in the sense of interpreting probability as uncertainty or something. It's just basically using the definition of conditional probability, which again is just a renormalization of a joint probability. So all the information about how likely certain co-occurrences of data and parameters are already encoded in the joint distribution. And the joint distribution then can be formed obviously by the prior, so the marginal about the parameter, and the conditional of the data given the parameter. This we briefly mentioned was not that crucial, and this is kind of the main thing that we took from yesterday. So we have this joint distribution, this probabilistic model. That's the starting point. Usually it's formulated in terms of a prior distribution and a likelihood. So instead of just writing down the joint distribution, we write down the prior distribution and the likelihood, but this then defines the joint distribution. We have this joint distribution, and then we are interested in Bayesian inference in deriving the other conditional distribution, namely the parameter given the data, and for model comparison, the marginal likelihood, which is the marginal distribution of the data. and for a given, and this is of course always important, that you distinguish that in terms of the probabilistic model, the prior distribution, and the likelihood. There it makes sense to think of all possible values of y, but of course in the application of this model, and when it comes to the posterior distribution and the marginal likelihood, y is something that is observed. It's a single value, and we have one single posterior distribution for this single data value, and we have one number, so either probability density or probability mass for this marginal likelihood of this data point. But of course, the whole thing is always formulated so that it works for any data, but in the application, of course, you have one observed data set. And then finally, we discussed inference summaries, and we discussed that the expected value of the posterior distribution is the base estimator that you sensibly use if you use a squared loss function. We discussed all that. One thing I want to point out, because it will come up in the slides today, is that this is also called the minimum mean squared error estimator, MMSE. That's just another name. It's squared error because it's the deviation between the estimated value and the true but unknown value that goes into the loss function. So that's the error. So it's and then it's the expected value. So that's the mean, although it's always bad to confuse expected values and means, but that's how this is called. It's the expected value of the posterior distribution, and it also has this name MMSE estimator. The abbreviation will come in later, so that's why I want to highlight that. And another thing one can do is to take that value of the parameter that has the highest density or probability mass in the posterior distribution, and that's called the maximum a posteriori or MAP estimator. And that is the base estimator that follows from a 0-1 loss function. And finally, we discussed Bayesian interval estimation, essentially by stating, okay, we have a posterior distribution, and then we can, for each interval, can say, okay, our uncertainty, of course, uncertainty is another word for certainty. Our certainty, it's just the kind of opposite, obviously. Our certainty that the parameter takes on values between 0 and 2 is then, by integrating, for example, the probability density function is 0.3, something like that. Or we say, okay, with 95% probability, the parameter takes on values in between these two bounds, which is quite a high probability. So that's almost certain. So we are quite certain that the parameter takes on values, I don't know, between -2 and 2 or something like that. Good. So that was what we did yesterday, and that's where we continue. Before we continue, are there questions that now also reviewing that you would like to clarify?
Just with what you said last, with kind of the what would be in the frequentist way the 95% confidence intervals. We talked yesterday that it's not as simple with when the distribution is not symmetric. Would you still do it in a way that you basically have two tails to each side that have 2.5% probability kind of, and try to estimate it that way? Or is it like way more complicated than that?
You have, like always, also in confidence intervals, so everybody's used to these confidence intervals for the parameter of a Gaussian distribution, where you then multiply the so you have the mean, and then you add the t-value times the estimated standard error or whatever. I have to teach. I will teach it again in the winter term. Look at my lecture from last year. So everybody's used to that, but there are also in this setting there are already many more options as soon as you go away from the Gaussian. So you can. So one way to do is to find the biggest interval that contains 95% of the probability mass. So in terms of the length of the interval, that's one option. And that doesn't need to be symmetric. That depends on the view or on the form of the probability density. What's another option? So there's maximum length, so maximum size. Yeah, I mean you can come up with all kind of, so can also come up with maximum symmetry about the mode or something like that. So it's yeah, I don't have all the options right now in my head. It's just that that there always have been more options than cutting off 2.5% in the upper tail and the lower tail. So yeah, maybe if you're interested in that, join our confidence interval lecture, and maybe I have something more to say about that. It applies here the same way, but it's then often not that easy to actually find these interval boundaries, because you might have to shift them around quite a lot, and you do this in a numerical optimization framework, and then it gets more complex. Yeah. So that's what I can say about this right now, because I don't have more on that prepared in my head right now.
Okay, thanks.
Any other questions?
Yes. I have one question about the new notation for the probabilistic model. Maybe I'm just overlooking something very obvious, but so the V is the random entity, the observable, right? It's on a slide in the foundations, like one of the first slide 7 or so.
It comes up here as well. So there's this V. The V is actually, the V is an epsilon. That's the Greek epsilon. It just looks like a V. So I wanted to, so I'm using, and that's what confused me yesterday a little bit. When you look into the applied literature on Bayesian inference, this distinction between random variables and the values that these take is not necessarily clear. But of course, in the whole curriculum that we are doing, we make this very clear all the time. But here it wasn't quite there. So now it's there. So the var theta, so this thing here, oops, my mouse is not working. That's also good if we switch to online. The var theta is the random entity, and the theta that you see here also in the joint probability mass function density, that's the value that it takes, and the same for the epsilon and the other epsilon. Okay, but back to your question.
Okay.
Yeah,
I think it's clear enough for me. Okay. Thanks.
Yeah, the thing is in probability mass function and probability density function, unlike probability distributions, they are really functions of values. Yeah, so one writes probability distributions always with respect to the random variable, and then you have this thing P of C equals X is 0.1 or something like that. But into probability mass function, probability density function, you just put the values. And this is why this notation, like it's here in equation 1 on this slide, P theta Y makes sense, but it's important to realize that theta and Y are values that the random entities var theta and Greek epsilon can take. And I also, so one way to establish that, I mean, we will see that in the winter term all the time. One way to do that, or the way it's typically done in probability theory books, is to use large or capital, to use capital letters for the random variable and lowercase letters for the values that they take. But that doesn't work if we also do GLM at one point, because usually in probability theory, you don't have to deal with, or in the basic probability theory, you don't deal with matrices. But if you at the same time at one point deal with matrices, and you have this convention that matrices have large or capital letters, and random variables are distinguished by capital letters, then you have this double thing. So my convention is now, and this is what I worked in, I already did that in the preparation for this workshop, but not everywhere, as I realized yesterday. My convention is to use Greek letters for the random entities and Roman letters for the, or mainly Roman letters for the values that they take. As you see here, of course, theta is also a Greek letter, but that's just, it's just, the more you write, the harder it gets to, or the more you try to cover, the harder it gets to have a consistent and easy to follow denotation. Anyway, good. Any other questions? Okay, good. Then today we want to start with conjugate inference, and that's kind of the form of Bayesian inference or inverse probability that has been around for a long time, as we saw yesterday, also in the history bit. So that's what Thomas Bayes worked on with respect to actually the better binomial model in the 18th century, and which has then also been around for since then. Laplace worked on it, was labeled inverse probability, has been around forever. And in 2012, in a major historical event, Ostwald et al. Used the better Bernoulli model actually for modeling EEG data. So it has been around forever. And as we mentioned briefly yesterday, it has this nice property that everything can be done analytically, which is on the one hand nice because things are then definite and they're closed form solutions, and actually to do Bayesian inference means to add two numbers, something like that, and you don't have to turn on any numerical programs that optimize or create random samples or anything. But of course, the application and the application scope is also quite limited. So that's the downside. And yeah, that's how it is. And nevertheless, it makes sense to start with conjugate inference because one gets first applications of the Bayesian framework that we've seen now. So the first question is, of course, what does it mean? What's the definition of conjugate or conjugacy? And that's what's on this slide. And once we have this established, we look at the better binomial and the Gaussian example. So we start again from a probabilistic model like yesterday. So let this thing there, equation 1, p theta y, denote a probabilistic model with conditionally independent, identically distributed observed random entities, epsilon 1 to epsilon n, and not directly observed, and typos, and not directly observed random entity var theta, or maybe without the A, I don't know. So that's exactly the same setup as yesterday. So this assumption of conditional independency is not completely crucial. Well, for conjugacy it might be, but it's already making the model more specific. The important thing here is that we now talk about a family of distributions of theta, so the parameter, and family just means a set, many distributions. For example, all the beta distributions that we already seen yesterday. Then this family phi is called a conjugate family of distributions with respect to this likelihood, this py given theta, if the posterior distribution p theta given y is an element of this family, irrespective of the prior distribution. and the observations. And irrespective of the prior distribution means that regardless of the precise prior distribution, of course, it's in the same family. So, for example, the family of beta distributions. But for all of the beta distributions that you can use as priors and all possible observations that you can make, the posterior is again in the same distribution class. So to make this concrete, the prior is, for example, beta, and the posterior is also beta. Or as we see in the other example, the prior is Gaussian and the posterior is also Gaussian. Or in the Dirichlet model, the prior is Dirichlet, which is a generalization of the beta distribution to vectors essentially. And the posterior is again in a Dirichlet distribution. That's called conjugacy. If this whole thing is so such a conjugate family is also called closed undersampling. Yeah, whatever. And the one thing to realize here is that usually in these models, these are the same kind of low-key parametric models like in frequentist inference. They usually have parameters. So you know that the Gaussian has parameters, as the expectation parameter and the variance parameter. We already seen briefly yesterday that the beta distribution has parameters. And then one has a little bit the problem that there are two kinds of parameters. So one thing is this theta parameter that one wants to do inference about. And then one has other parameters that refer to the distribution on this parameter that one wants to do inference about. And then sometimes these parameters of the prior and the posterior are called hyperparameters. Sounds fancy. I don't find it too useful because it's easier to say, okay, the parameters of the prior distribution, the parameters of the posterior distribution, because you also can have more than these kind of three distributions, so the likelihood, the prior and the posterior, and then at one point you get lost, or you maybe you want to also put a prior or put a prior on the hyperparameter, and then you can call it hyperparameter for this decision, but then you end up like, what was it called? Gap kinase. It's just, I don't know. So I don't use the term hyperparameters too often. The important thing here is in conjugate inference, the prior and the posterior distribution are of the same type. So prior beta, posterior beta. The one thing that we will see how this then works really is that these are, of course, of the same distribution type, but usually they have different parameters. I mean, it wouldn't really help us much, or nothing would happen if our prior is a uniform beta, and then we observe some data, and we actually observe some data, and the posterior is again a uniform beta, and then nothing happened. I guess one can conceive some weird scenarios where this may happen. But it can't so in the beta binomial model, it actually can't happen. If you make an observation, something changes. So and these parameters are then computed from the prior parameters and the data. And this update formula for the hyperparameters, the parameters of the prior and the posterior, these update formulas, so how you get to the parameters of the posterior distribution, that can be found analytically. And this is what I want to show you now. But this is, there are more models than conjugate models than the beta binomial model and the Gaussian model. Specifically, you will see when we do the Gaussian model that you feel like, okay, but the Valence parameters assume to be known. This is like Z-test. I don't like this. Yeah, there is also the Gaussian gamma model, which is a conjugate model for the Gaussian, where both the implementation parameter and the variance parameter are unknown. In the end, I have a little list. I mean, one can, maybe I just jump to that list now because I'm talking about it anyway. There are many conjugate models. So the generalization of the beta binomial is the Dirichlet multi-nulli. Generalization, or treating everything as unknown, is the Gaussian gamma Gaussian model. This whole thing in terms of Gaussian conjugacy can be generalized to multivariate models. So we will only look at the univariate case, but of course also for the GLM, one can have where one has, I hope you all know the GLM with the beta parameters, which are, or however you want to call them, but you all know simple linear regression, that you have an offset and a slope parameter. And if you put them into a vector and call this vector beta, then that's a beta parameter vector and it's two-dimensional. So you have a two-dimensional distribution, and of course there you can also use a Gaussian prior, and then you have the multivariate Gaussian model, or in the same scenario you might also have the covariance parameter, so the covariance matrix parameter unknown, so you need a prior over the over a covariance matrix that also exists. It's called the Posterior Distribution, and yeah, all of this exists. One can actually, for a large class of probability, so parametric probability distributions, one can establish a general theory. I think beta binomial is not in this thing, but all the Gaussian models are, and many more. And that's in conjugate inference in the exponential family. So there are many probabilistic models where you can specify a prior distribution and a likelihood, and you can do Bayesian inference using closed form solutions, or using hyperparameter update formulas or whatever, and one doesn't need any MC or any variational inference to do Bayesian inference there. And yeah, to make this really concrete, I want to discuss the beta binomial model in some depth, and then also the Gaussian model in some depth. Are there questions right now? Okay, then let's get started with the beta binomial model. Maybe as a brief motivation, again, so we looked at parts of this yesterday, but I want to talk more about it and go a little bit more into depth. So as a motivation, this is kind of this clinical study example. So we are interested in the effectiveness of a treatment, which as outcomes can be a failure or success. So the outcomes are 0 and 1. And we want to infer on the probability, that's here the theta. It's not always that the theta is a probability, or can be interpreted as a probability. For the Gaussian model, the theta has nothing to do with probabilities. That's the expected value in the variance parameter. But here it is. If you are interested in this, Google imprecise probability. That's kind of a generalization of this whole business, and it gets out of the whole probability theory framework. And that's kind of pushing this idea of reasoning over probabilities more. It's interesting, but nothing that I worked deeply with. So here, one is interested in this parameter theta true but unknown, which is the true but unknown proportion or probability of success outcomes. Proportion. Oh, well, I had my reasons for writing proportion there, not probability, but I think I didn't want to confuse things too much with too many probabilities, but it's the probability of a success, and you want to know how high that is. And that's a reasonable question. Yeah. So like we discussed yesterday with corona vaccination, so how often does it help? And that what's the proportion, what's the probability that it helps? And if you know that it's more than 50%, that's good. If you know that it's less than 50%, well, it always depends on whether it's good or not on the utility of that you then assign to these estimates. But but first you need to, of course, get an idea about that. And the example that we discussed is a typical study example, 30 participants, and now we have an observation, and we want to quantify our uncertainty prior and posterior. And that's what we do now. And we also want to look a little bit of how the mechanics of Bayesian inference then work. So I start here with the description, and we discussed that yesterday with the description of the likelihood model. And that's always important to keep in mind, although this is then a conditional distribution, it's conditional in the sense, or because one of its aspects is a random variable. In this case, the theta becomes a random variable, but of course, that doesn't need to be the case. Theta can also not be a random variable. And then it's just a binomial distribution with a fixed parameter, and it has this analytic form. Sorry, I can't point right now. As soon as I point, I get to the next slide. Maybe does this work? No. But maybe have a look at 2 and 3. So in 2, it's just the definition of the probability mass function. So we put in a value for y, which were these sums of successes and failures, and then can evaluate the probability mass that is assigned to y according to this formula there. We need to specify, to evaluate the formula, we need to specify n and theta, and then we can just evaluate this binomial coefficient there, and then do theta to the power of y and times 1 minus theta times to the power of n minus y. And the in terms of notation, you see then we write epsilon is distributed according to the binomial, and below that the probability mass function. So the thing that you see on the right hand side in 2 is abbreviated by this bin y semicolon theta comma n. So this bin for binomial y semicolon theta n is just a short form for this formula, that you see there. And that will be important in a second. So that's really the probability mass function. It's a function, and it's the argument is y, and the parameters are n and theta. And we looked at this yesterday already. So the interpretation is that this theta is the probability that on a single trial 1 comes up, success, and because it's a probability, it's sums to 1. So 1 minus this parameter is the probability that 0 comes up. The other thing, so that's what we use as the likelihood. So that's for a given value of theta. That's what we assume the data distribution looks like. So if we, in our example, we can look here, if we assume that the parameter theta is 0.5 and there are 10 trials, then the probability masses assigned to the different values of that y can take are as shown in the center graph on this figure. Now we want to also establish a prior, and for this we introduced yesterday already the beta distribution and also its density. Again, first in terms of the intuition, the beta distribution, which of course you don't encounter. Well, there are good reasons for actually encountering this in frequentist statistics, which I don't remember, but usually you don't. So the crucial thing here is that it's a probability distribution of a continuous random variable that takes on values between 0 and 1, or let's say that only has non-zero probability density on the interval between 0 and 1. So it's allowing to describe uncertainty over this probability parameter of the binomial, and depending on its parameters, which I here call alpha and beta, it looks different. So the formula for this, for evaluating this, you see in 4. This is now a function of theta, and the parameters, which you can also call hyperparameters in the Bayesian setting, are alpha and beta. So if you have, if you fix alpha and beta, you have to evaluate the gamma function, which is just a function, Google gamma function, and you can look it up, it's just a function, and this gives you some numbers for alpha plus beta and for alpha and for beta, and then you evaluate this theta to the power of alpha minus 1, 1 minus theta to the power of beta minus 1. And again, we abbreviate this probability density function in 5 with this beta theta semicolon alpha beta. The question, we will see a little bit about the meaning of alpha and beta later on. So maybe we do it there, because you can interpret that later on as virtual observations that you made. So, but that gets clear once we have the whole posterior inference in place. 2 things to note here is we didn't introduce that the binomial could have, but of course everyone is very familiar with the expected value of a Gaussian, which is the mu, and the variance of a Gaussian, which is the sigma square. But that's not always the case, that the parameters are just the expected value and the variance. And of course, if we want to use inference summaries, we need expected values, and here the expected value of a beta random variable is given by alpha divided by alpha plus beta, and the variance is a little more involved. That's alpha times beta divided by what you see there for the variance. And of course, it's not easy to see that, so there you need a proof, because you know that the expected value is defined as an integral, and the variance as well. And you can look up these formulas in terms of the parameters for expected value and variance on Wikipedia. And the proof, you have to dig a little bit deeper. One beta distribution. So in terms of the alpha and beta, so this alpha and beta, they need to be larger than 0. If it's 1, 1, if they are 1, 1, then you get the uniform distribution on this interval from 0 to 1. If they are smaller than 1, you get actually high probability density towards 0 and 1, and low probability density kind of at around 0.5. It's not that interesting, although it's actually interesting if you are interested in Jeffrey's priors, which are from the Jeffrey criterion of invariance, transformation invariance, the uninformative priors from the intuitive approach, the uniform, so the beta 1, 1 is an uninformative prior. If the alpha takes on larger values than beta, you see this, so don't get confused, the alpha and beta, I mean here, so if the alpha here is 3 and beta is 2, then there's a shift of probability density to larger values of theta, and the other way around. I didn't show that here. And if this difference is larger, so if it's 10 and 5, as you see on the right-hand side, it becomes more, even more centered and more, maybe even a little more shifted. And in terms of the expected value, that's alpha divided by alpha plus beta. So 3 divided by 5 in the middle graph, or actually in the leftmost graph figure, it's 1 divided by 2. So the expected value is 0.5, which kind of makes sense. If you have 3 divided by 5, it's a little bit more than 0.5. If you have 10 divided by 15, that's even a bit more than 0.5, but that's how these parameters relate to the expected value quite straightforwardly. Good, and that's a good point for a break, because then after the break, I can discuss the better binomial model in all its glory. Any questions right now? Good, then let's have a break. Good, so this is then the entire magic of the better binomial model on one slide. We have now everything that we need, hopefully, installed. So we consider a probabilistic model, py theta, which we formulate in terms of a conditional distribution and a marginal distribution, conditional of y given theta, so data given parameter, and marginal of the parameter, and called prior distribution. And we use for the likelihood the binomial, because we want to model this phenomenon of observing k out of n successes, or better, y out of y successes out of n trials. In the example, 30 trials or experimental units or participants, and 18 observations of ones in there. And the n for the binomial that we treat as a fixed parameter. We could also, now let's not go into that, but there are different ways to do things, and then n can also be a free parameter, but here we just say, okay, we want to use, we have 30 participants, and now we say before observing data, so our prior uncertainty about the parameter theta is specified in terms of a better distribution. And we know what these things are. And then the result is, and where the result comes from, I will show you in a second, but then the result is that the posterior distribution of theta given y, so the other conditional distribution in this probabilistic model, is given also by a better distribution, which then means that we are dealing with a conjugate model, because it's again the same class of probability distributions, but with different parameters. So the prior distribution parameters, or hyperparameters alpha and beta, are updated, as you see in 7. Alpha, the first parameter of this posterior distribution is alpha plus y. So if we had alpha being 1 before, and then we observe 18 successes, our first parameter for the posterior beta distribution is 19. And the second parameter is updated essentially by the numbers of failures that we observed. So remember that y is the number of successes that we observed, and the number of failures is then the number of the total number of trials minus the number of successes. So beta plus n minus y, and that's the posterior distribution. And then we can, of course, like yesterday, have inference summaries of the posterior. Of course, we can also then have credible intervals. Here I'm just focusing on the point estimators, and namely the two base estimators that we established, the minimum mean squared error estimator, so the posterior expectation, and the MAP estimator, so the maximum posterior estimator. So before we look what that means, or not what that means, that's hopefully relatively clear, but why this is the case, before we look into that, let's continue with the example. So we assume, because we are somewhat naive, we assume that our prior is this uniform, so basically stating all possible probability values for a success on a given trial have the same probability density. So we don't bias our model and our estimate into any direction. We just say they are all can be anything. So whether that's the most sensible thing to do and whether this is actually really non-informative are bigger questions that we don't explore here. But yeah, naively, we can say, okay, that's the same probability density for all possible values of this parameter. So we don't put any information in there. We use an uninformative prior. And that you see on the left. And then we make an observation. And here the observation is, so we consider a study with N30 experimental units and observation of 18 success outcomes. And then we now have the formula to describe our posterior uncertainty about this true but unknown theta parameter. And it's updated as given in this formula. So the prior parameter alpha plus y, that's this 1 plus 18, and the beta prior parameter plus 30 and minus 18. And if I didn't do my arithmetic wrong, we end up with a better distribution with parameters 19 and 13, and that's shown there on the right-hand side. So that's then the posterior uncertainty about this theta parameter. And of course, we, if one looks at it, we see that, yeah, the map is definitely, so the highest probability density is around 0.6. And the expected value, I mean, I have it here, is a little bit smaller. So it's 0.59, which we just get from the formula for the expected value of a better distribution. So that's then our posterior uncertainty and our point estimates. In terms of credible intervals, I have here an example that we asked what's the probability that this unknown parameter takes on a value larger than 0.5. And this can be, of course, that one, we just need the cumulative density function of the beta distribution, which I hope you know what that is. It's not the formula, but at least the CDF, but that's, you might remember that this is refers to the probability for the random entity to take a value smaller than the value that you put in. So the probability that var theta is larger than 0.5 is 1 minus the probability that var theta is smaller than 0.5. And this probability var theta is smaller than 0.5, that's the probability density, the cumulative density function evaluated at 0.5. For this, there's a formula, or it's implemented in R or whatever, and we get 0.14 out. So the probability that var theta takes, or this parameter of the binomial takes on a value larger than 0.5 is 0.6, which looking at this also makes sense. It's not 1, but there's much more probability mass above 0.5. And prior, it was, of course, if you look to the left, it was 0.5. So that's then something one can infer from this, and that's it, essentially. So in terms of scientific inference, I think that's it. That's then what you can say. And then somebody can base a decision on that or not. But you've quantified your uncertainty. You're done. You can go home to the next project. For yeah, this is then the last thing here in 15. This is something that I mentioned yesterday already. Although I did not discuss maximum likelihood estimation for the binomial or the Bernoulli distribution. You might know that maximum likelihood estimators usually or often end up as means. You know that from the Gaussian very well. The same holds true for the Bernoulli distribution, and for the binomial, it's not really the mean, but it's y divided by n. I guess that's the maximum likelihood estimator. For a single trial, the maximum likelihood estimator, so the frequentist estimator, the frequentist point estimate best guess would be 1. We discussed it yesterday a little bit. And for in the Bayesian scenario with the same prior, that would be 2/3. So you one thing to realize here also from this update formula in terms of this alpha and beta parameters of the beta distribution. So if you look there where it says 1 + 18 and 1 + 30 - 18. So 18 is obviously the observed number of successes, and 30 - 18 is the observed number of failures. So 12. 12, yeah, 12. And these alpha and beta hyperparameters, so the ones of the prior distribution, so 1 and 1, from this update formula, you see that they are essentially the observations of failures and successes, or successes and failures that you did not do before, but you somehow assume to have done before. So that's what they are sometimes called virtual observations. And of course, if you now use different values for them, then it is like, so for example, if you use a beta distribution with parameters 19 and 13 as a prior distribution, it's like you made 19 success observations and 13 failure observations. So this is the interpretation or useful interpretation of these alpha and beta hyperparameters of the beta random variable. Because from the formula, it's not really clear what this means, but from this idea of updating the beta distribution, it gets very straightforward of what these alpha and beta things mean in the beta distribution. Yeah, is there something else to say about this? In terms of this thing with the maximum likelihood estimator and the posterior expectation, so the last thing here in 15, of course, this difference is quite large if you have very few observations, but if you go to more and more observations, then of course the effect of the prior disappears. That's also, so these are all nice features of Bayesian inference. So of course you can say, I don't like priors, but the thing is the prior also washes out if you want, because if you look at the update formula, if n gets very large, then and you have alpha and beta being relatively small numbers, so fairly low prior certainty, then this alpha and beta, if y then becomes a large value, or n becomes so if n becomes large, then regardless of y, if n becomes large, then beta plus n becomes large, and then you either subtract a lot and then beta comes small again, or y is also large, so you made a lot of observation, and then this alpha plus y is also a large number. So and then in the end, it's in terms of difference from the maximum likelihood estimator, it's not that different, because then if you look at this formula here in 8 for theta MMSE, you see alpha plus y divided by alpha plus beta plus n, and the maximum likelihood estimator is y divided by n. And if n gets large, then the effect of alpha and beta just becomes very small. So it's really what this just shows is that of course more data helps, and it's doing a lot of sensible things that I think one wants to do if one is kind of faced with this inference problem or this kind of scenario that one can model by a better binomial model. What else can I say about this? It's not shown here, but you might know this prediction error perspective on things. So with Kohler-Wagner models, which cognitive neuroscientists love. So one can also show, that's not here, that you can formulate sequential better binomial updating as a predictive error updating scheme with the feature that you weigh the observations by 1 over the number of observations that you made, which means that if you already had made a lot of observations, so let's say you have made 100 observations and you have 50 successes and 50 failures, and then you make another observation, then you don't shift your uncertainty a lot, and specifically much less than if you have very few observations. So just a side note, but it's all of this makes intuitive sense. I always think, one can say, okay, I don't like it for some reason, but it makes sense. I mean, what else do you want? And if you want something else, then design something else, but this is pretty nice. The question is a little bit, of course, why it's like that. So why this update formula? And this is what I also want to discuss then in this proof. But are there questions right now before we go into the proof why this actually holds?
I was just thinking about the comparison between the maximum likelihood and maximum R posteriori. Would you say that thus it might make more sense in the light of very few data points to take a Bayesian approach compared to a frequentist approach?
Yeah, because I mean, so the problem with the frequentist approach in light of few data points is that because you only ever end up with point estimates, but okay, you cannot do confidence intervals in frequentist, but nevertheless, the point estimate that you end up with, you have like yesterday, you throw a coin and you come up with heads, and the frequentist, so the maximum likelihood estimates, then says the probability for this coin to come up with heads is 1. So because that's the inference that you do based on this, and this is of course it's a very strong claim after seeing just one observation. So, and of course you can say, I think it's just an overly strong claim that you come up with in frequentist statistics. So what we will see, this is also what, this is actually the same thing. Maybe I can mention this also in answer to this question. So the posterior expectation, one can slightly reformulate that as you see here in 9, and it adds up with this formula where you have this alpha plus beta divided by alpha plus beta plus n times, and that's the important bit, times alpha divided by alpha plus beta. That's the prior expectation. And then you have another thing, and then it's times the maximum likelihood estimator. So you weigh your prior and the maximum likelihood estimator to come up with your parameter estimate. And you obviously also see there that you weigh the maximum likelihood estimator, the more data points you have. So it just, it's just a reasonable way to go about things, that you say, okay, I haven't seen data, I think this is what's happening, and now I have seen data, and now I think that's what's happening. And in the frequentist, you somehow don't want to admit that you have you don't want to admit that the world started before you do your experiment, and you just saying the universe just started when I did this experiment. But of course, that's never the case. I mean, you do experiment, so the next experiment is always built on everything that humans did before. Anyway, so yes. Yes, of course, Bayesian inference makes a lot of sense. Okay, any other questions? Questions, of course. So it's really simple. So if you implement this, it's really simple, right? So you just need, so the only thing that happens is that you specify alpha and beta as your prior parameters. You make an observation in this case, which is just a number between 0 and n, and then you do alpha plus y and beta plus n minus y, and then you are done with inference. So you don't need to do MC, variational inference, or anything. You just have everything, and it's there. The question is, of course, why this holds. And this is also not that complex, actually. That's what is shown here. And of course, it has to do with the functional form of the binomial and the beta probability mass and density function, respectively. So the way this proof works, of course, the question is, how do we get the posterior distribution? Well, we know that up to a proportionality constant, the posterior distribution is equal to the likelihood times the prior, and more specifically, of course, the probability mass function of the likelihood. So the bin y semicolon theta n in 10 times the prior probability density function, which is this beta distribution. And what we are ignoring here, so we only consider, of course, what you of course need to keep in mind is that the prior and the posterior, they are both functions of theta. So everything that is not does not depend on theta for the moment we ignore. So in terms of the beta random variable, we ignore this gamma factor here, which is actually there to normalize the density function. And in terms of the binomial, we ignore this coefficient n over y, because we just look at the things that actually where a change in theta actually makes a difference, because we want to obviously look at probability density function, probability density as a function of theta. And so again, in 10, then in the third equality, but it's a proportionality statement, so the constants are ignored. We just put the functional form of the binomial without the n over y, and the functional form of the beta, but without the gamma term. And then, yeah, we see that we have fairly similar things. So theta to the power of y, 1 minus theta to the power of n minus y, times theta to the power of alpha minus 1, and 1 minus theta to the power of beta minus 1. And then we just need the rules for dealing with Potenzen. I don't remember the English name right now. So dealing with these power things. And of course, you know, if you multiply theta to the power of y with theta to the power of alpha minus 1, that's the same as having theta to the power of alpha plus y minus 1. So Potenzregeln. And the same goes for this 1 minus theta term, so n minus y plus beta minus 1. I rearranged the order of the summation there a little bit, but that's it. So we now know from what we see in 10 that the posterior density is proportional to theta to the power of alpha plus y minus 1 times 1 minus theta to the power of beta plus n minus y minus 1. And then what is helpful here is that if we look at the beta distribution, we see that the beta distribution looks very similar. It has this theta alpha minus 1 and 1 minus theta to the power of beta minus 1. The question is then, what are our alpha and beta in this thing that we have established here? And that's, so this is why I also rearranged terms previously. So then our hyperparameters are alpha plus y and beta plus n minus y. So the kernel, I refer to the kernel of the PDF, I just mean the thing that depends on theta and not this prefactor. So by looking at this, so in principle, what we would have to do here is, then also to find the integration constant, but because we know how the beta probability density function works and what the integration constant is, this is this gamma factor. In terms of the Gaussian, it's this 1 over the square root of 2 pi sigma square. We don't have to do anything. We basically can read off from multiplying the likelihood and the prior probability mass and density function respectively. We can read off the posterior density function. And that's where these formulas come from. So essentially, they just come from how to deal with powers and from plugging in really the probability mass function, the probability density function into Bayes' theorem, or at least the numerator of Bayes' theorem. And then the expected value and or the MMSE and the map estimators, they again just follow from the properties of the beta distribution with then just the parameters that are then there in the posterior, so in 11. So in 12, it's just a rehearsal of what the expected value and the mode of a beta distribution with parameters alpha and beta are, and if alpha and beta are alpha plus y and beta plus n minus y, then we get to these formulas for the minimum mean squared estimator and the map estimator. And that's where this is coming from. So it's also not that tricky to to find the analytical solution here. Of course, it rests on that one already has found how to normalize this kernel of the beta PDF, namely this theta to the power of alpha minus 1, 1 minus theta to the power of beta minus 1, that this works with the gamma function. That's the hard work there. So to find this, to solve this integral, because that's the integral of this thing, to the power of minus 1. But this is, yeah, of course we could also discuss that, but we don't do that here. Yeah, so that's the beta binomial model, and that's one model that one can use for Bayesian inference. Of course, one cannot use it in any scenario, but one can use it in any scenario where you have outcomes, where you have where you are interested in the probability of success versus failure, and you have multiple observations. That's when you always can use it. But of course, it refers to, and this is of course for at least cognitive neuroscientists. So it works in a way. This is something that works for decision neuroscience, I would say. If you have decisions that you take, and you only have two decisions, and it's you have 0 and 1, and that your decisions, one can use it. Of course, it works very well for medicine. It works very well, I don't know, for military use. If you want to figure out how often you hit the target or you don't. It doesn't really work out if your data is not binary, but you have, for example, MR signals. Of course, you can threshold everything, and then you also always have binary things. But yeah, it doesn't feel that natural to apply the beta binomial model to, I don't know, the average MR signal at a specific location, averaged over participants or something like that. That doesn't feel that natural. So it doesn't solve everything. It's not the nicest model for all scenarios, but for these scenarios where you have binary data, it works. And if you have kind of categorical data, so more categories than 0 and 1, then it makes sense to use the Dirichlet multinulli model, where you then encode each category by a vector of ones and zeros. So that's a natural generalization of that. Okay, questions about the beta binomial model? Okay, then I think we can also then start with the Gaussian model. Actually, there I don't know the history that well. I don't know it at all, actually. So beta binomial, as I said, has been around forever, starting the whole thing. At one point, somebody worked out the Gaussian. I guess also somewhere in the 19th century, 20th century, I don't know. So what are we dealing with here? So let's look at the example first. Here you can think of now the models that you know from undergraduate statistics, and specifically kind of, I don't know, t-test designs, one simple t-test designs, where you model data as being distributed according to a Gaussian distribution, and maybe even, being independently, so IID. So this very basic one simple t-test model, for example. Here because I always think everybody does cognitive neuroscience in the CBBS, which I don't think is the case, but here I used an fMRI example. So we are interested in the common expectation theta, so the expected value of a Gaussian, in multi-subject fMRI study with n participants. So the idea is so essentially it's doing one sample t-test on the second level in an fMRI analysis. For people who work with fMRI, you know what that is. If you are not completely lost in the classifier world, which would be bad. You are lost in the classifier world. Good. Sorry. So that's the basic idea. So one sample t-test. What we assume here, so that the proof or the whole model gets a little bit simpler, is that the variance of these entities that have this distribution is known. So we assume a known variance parameter. That's like in the what you might know then as Z-tests, and which is also a little bit useless, but it's more of deductive value to start somewhere where the variance is known. Of course, one can generalize this to unknown variance of the observables. That's then the Gaussian gamma model, but that's not what we have here. Tomorrow, in the variational inference scenario, we will do variational inference for a specific Gaussian gamma model. The thing is why I also don't like the Gaussian gamma model that much, the conjugate model, is that the Gaussian gamma conjugate model assumes a dependency of the, where is it? I think it assumes a dependency on either the variance on the expectation parameter or the other way around. I don't remember right now. I always find that very unnatural, so that you don't treat the parameters that you want to do inference about as independent, at least in the prior. Yeah, so tomorrow we will look at assuming independency for the expectation and the variance and having both of them unknown, but then we are actually leaving the conjugate world. That's tomorrow. So that's kind of one thing where this might come into play. So one sample t-test in fMRI analysis on the second level in a mass univariate fashion. And what we have here is, of course, then a likelihood that corresponds to a Gaussian. So this is why I brought up the Gaussian probability density function here again. And yeah, that's, I guess, more familiar to everyone. So it has this form 1 over 2 pi sigma square exponential of 1 divided by minus 1 divided by 2 sigma square y minus theta. So note that I write the expected value here as, or the expectation parameter, which you usually see as mu. I write it here as theta because our parameter that we want to make inferences about has been called theta since yesterday, and that's why I call it theta here as well. Yeah, it's the same logic as for the beta and the binomial. The probability density function is denoted in 17 by this ny semicolon theta sigma square. It's an abbreviation for that. The highest probability density is, of course, at the location of the expectation parameter, so theta, and you know that the width of the Gaussian curve, so the variance, is specified by sigma square. In this conjugate model, where we now assume a prior over theta and treat sigma square as known, we don't need another distribution, so we don't, or one can, of course, also use different priors for the expectation parameter, but here, and that's why it's called Gaussian model, we use a Gaussian prior over theta, so the expected value of our likelihood, which of course, we could also use a better distribution, but that would limit the possible range of values of theta, so the expected value of the Gaussian, to 0 and 1. The natural space in which the expected value of a Gaussian exists are the real numbers. It can be anywhere, so you can shift the Gaussian wherever you like. And hence, it makes sense to assume a Gaussian. No. So these are visualizations of the Gaussian distribution. I don't think these are new to you, so we don't need to discuss them. And I think this is again a good point for a break. So then after the break, we have a look at the univariate Gaussian model, and yeah, see how this works and why it works. Any questions right now? Good, then let's continue on this slide after the break. Then let's discuss the univariate Gaussian model. So this refers to estimating the expectation parameter of a Gaussian, and using for this expectation parameter using a Gaussian prior. And as we are in the conjugate model world, of course, it will be no surprise that the posterior is then also a Gaussian. How does the model look like? That's here described in 18. So our probabilistic model P y theta is again formulated in terms of a likelihood P y given theta and a prior P theta. And here a little bit a difference to the beta binomial is that in the beta binomial we assumed that we only have one observation, which was the sum of the successes. So we just observed one thing, and these were the number of successes in our n trials or n experimental units. And here it's a little bit more explicit that one could also formulate this whole thing for an average, but that's not what is done here. So here we consider each data point, and we assume that the data points, so the yi, are distributed identically and independently. So identically because we assume that all of them, as you see in 18 on the right hand side, all of them are distributed with the same expectation parameter. That's yeah, the standard assumption in this Gaussian IID sampling, that they all have the same variance parameter, sigma square y. And that they are independent. That, of course, refers to this factorization of the probability densities for each data point I over I to n. So that's this product symbol there. And yeah, so that's this IID sampling. We assume they all have the same expectation parameter. And for the expectation parameter, we assume a prior, which is also Gaussian. And this is parameterized by this mu theta and sigma square theta. Of course, if we have more than one Gaussian, and hence more than one expectation parameter and more than one variance parameter, one needs to keep track which variance parameter we're dealing with and which expectation parameter. Here the expectation of theta is mu theta, and even clearer, the different variance parameters have subscripts theta if they refer to the prior, and y if they refer to the likelihood. So that's the model setup. And then the result is given in 19. The posterior distribution, or the PDF of the posterior distribution, is given by P theta given y. It's again a normal, so there's the n. And then it's again a normal or Gaussian distribution over theta. Then the formula is a little bit more involved. Yeah, I think in the multivariate it also doesn't look that big. I don't know right now. Yeah, let's have a look. So first of all, maybe have a look at the variance parameter in 19. So the thing after the comma on the right hand side. So you see theta semicolon. Then there are two brackets with 4 terms, and then there's a comma, and then there's the variance parameter. So the variance parameter, the posterior variance parameter comes out as n over sigma square y plus 1 over sigma square theta to the power of -1. And this factor also, that's the same thing that you see for the posterior expectation parameter, but then multiplied with the prior parameters of theta plus the average of the data divided by the variance of the data. So we will look at a somewhat more intuitive formulation of this in a second. But what you should take from this right now, from this formula, is essentially the same as for the better binomial. So what plays a role in this formula for the parameters of the posterior distribution are the number of data points. So n plays a role. The variance of the prior plays a role, which of course in this case is, if you have a very small variance, then you have obviously very precise already in your prior, you have very low uncertainty. If you have a very large sigma square theta, you have a high uncertainty. And so because you assign probability density almost everywhere for theta. So the prior parameters play a role, the likelihood parameter plays a role, it's then, if you look at the formula for the expectation parameter, so this mu theta divided by sigma square theta plus n times bar y. Bar y is the average, so the sample mean of the data points, divided by the variance parameter of the data points. So you see that the data, so the bar y, so the sample mean is weighted sample mean is always weighted by the number of samples, so that's but it's mainly weighted by or it's crucially it's weighted by the data variance, so sigma square y. So if you have if the sigma square y, so the likelihood variance is very large, then the effect of the data on informing your prior distribution is less than as if it's very small. And that's this kind of weighing information by their uncertainty is also kind of a standard feature of Bayesian inference, and it's good and easy to see here. The point estimates, so the base estimators, are of course the same, so it's the expected value and the mode, which for the Gaussian, of course, both the expectation parameter. So what do we have here? So the prior distribution we discussed, the likelihood we discussed, as sigma square is assumed to be known, which is of course quite a restriction if you are coming from the frequentist world or just using this model, because why should you know the variance of the data? Usually you estimate that. As I said, one can do that as well. If one looks at this whole thing more in terms of sensor fusion aspects and so on, then it sometimes is not that bad to. So if you have multiple forms of data that inform something, then assuming that you know the variability of the data doesn't hurt that much, but that goes into Bayesian sensor fusion. Credible intervals, again, can be derived from the posterior with the CDF. And yeah, so the posterior expectation in 21, you see basically you see that here, so there's a proportionality constant, which is this thing in the brackets to the power of -1, but then it's essentially a weighted form of the prior expectation, so mu y, and the sample mean, so which is of course also the maximum likelihood estimator, and both of them are weighted according to their variance parameters. So if you have a small prior variance, so if sigma theta is quite small, then of course 1 over sigma square theta gets large and you give more weight to the prior. So if you are very certain before you see some data what is going on, then this is respected by the inference or the hyperparameter update formula. And the other way around, if it's low, then it doesn't play much of a role. The variability of the data goes in, as I already said, and yeah, the number of data points as well. So then, yeah, what I always, when we now look at an example, what's a little bit hard, I always think, in terms of Gaussian models, is to now really wanting to have. So one cannot, so a Gaussian that is uniform does not exist. Yeah, so one cannot have infinite variance on the Gaussian. So you cannot have a uniform prior, which is Gaussian. So you can use a uniform prior, but then you don't have a Gaussian prior. And you end up with something that we wrote about in the paper some years ago, so I don't remember right now what happens then. But if you really use a Gaussian, the variance parameter needs to be finite. One gets around that somewhat, so you can use, if you reparameterize that and use precision, so 1 over variance, you can use 0 precision. That works. Yeah, but how does that lead to a uniform? I also don't think it leads to a uniform. So the problem is, so to have something that is uniform in terms of the Gaussian does not really work as a prior. But of course, you can make the variance very large, and then you're almost at, so you have put very little weight on the prior. So that's one thing there. Yeah. So if one really wants something uninformative for the Gaussian, there are different approaches, but that goes beyond what we are doing here. So because the question is always what's uninformative, and uniform is not uninformative. So that is the intuition that we use for better, but it's actually the uniform is not uninformative, because once you square something, then you assign different probability to different parts, and then you need to think more, what does uninformative really mean? And then there are approaches like Jeffrey's priors that are invariant under transformations and so on. So although one does not get to the uniform here, I'm always fine with that in a way, because it's not uninformative anyway. So then we just use something that feels fairly uninformative if we use a wide prior. If we want to use an uninformative prior, that's of course not, that's not a necessity. Here's the example, then continued. So we now here assume that we have 12 experimental units, so participants, and a sample mean of 3.14. And yeah, then I try to put in, and we use a prior parameters for theta of 0 and 10. So then this variance parameter comes out as roughly 0.16, and the posterior expectation parameter comes out as 18. That was not, maybe I'm right, maybe I'm wrong. Why does it confuse me? Let's have a look. Oh no, sorry, that's not, sorry, I was confused. That's not the, so in 32, that's not the posterior expectation. That's just part of the posterior expectation, which is then, of course, weighted by 0.16. So here we have, in 33, we have then the posterior parameters for this scenario, where we observed as an average 3.16, 3.14. So the posterior expectation here comes out as 3.01, and the posterior variance parameter is 0.16. So you see that the sample mean says 3.14, and the posterior expectation says 3.01. So it's still somewhat biased to the prior of 0, which was the prior. It's not strongly biased there. The variance was 10. Of course, if we increase the prior variance, then we would in the end go even closer to the sample mean. So if you want the sample mean to be the posterior expectation, then yeah, you can do that. But that's then, yeah, you can do that, but then you also didn't gain much from the whole Bayesian inference procedure, because you didn't inform. So that's then, yeah, then you have uninformative prior. It's good, special case of Bayesian inference essentially, but you didn't gain anything by using Bayesian inference. Yeah, so the point estimates are 3.01. What did I include here as well? Yeah, so the probability, the posterior probability for theta being larger than 0. Why do I use this posterior probability for larger than 0? Because, of course, Gaussian and this IID sampling of n samples, that's very close to one sample t-test, or in this case, because the variance parameter is known, z-test. Then it's kind of interesting to see what happens. So the probability for the expectation parameter to be larger than 0 is roughly 1 with this posterior probability distribution that you see here also on the right. So you see all the probability mass between 2 and 4. And the Z statistic actually for the same thing, because of course you can also compute a Z statistic for the null hypothesis parameter of mu0 being 0, would come out as 7.69, the p-value of 0. So yeah, in terms of whether you have, you can reject the null hypothesis, there is no difference. So that's also what I meant yesterday. So if things would look different, so if our sample mean would be 0.02, the Z value would be quite low, but then also the posterior expectation would be quite low, and the posterior density would be centered around 0 as the prior. So if you have very little signal in the data, it's not that Bayesian. So that's actually not what I'm showing here. What I'm showing here is if you have a lot of signal in the data, then z-test and Bayesian inference tell you the same story. The other way around, if you have very little signal in the data, they will also tell you the same story. So it's not a remedy for null results. So the remedy for null results is the appreciation of null results. And the remedy for null results is documenting clearly what you did, and people appreciating that you did proper work, and that there's a null result, and that they then know that, and then can say, okay, maybe then I don't go down this route because there's a data point that says the study that there's a null result. Maybe I still believe that it must be the case. So then I do an experiment that is similar, And if I then also get a null result, maybe then I believe that it's actually, there's really no effect. Or I see an effect, and then I can try to understand why I see this effect. But the remedy for null results, and people say you cannot publish it, is not Bayesian inference. It's just being happy, and the remedy is doing good work. That's the remedy. Anyway, yeah, so that's basically the result for the Gaussian model. But it's again, of course, not the question of why this is the case. That is what is here in the proof. One thing that I forgot to say, the posterior Valence parameter is reciprocally related to the number of observations. So the higher the number of observations, the lower the uncertainty. That's also, of course, nice. So you see the n goes in there, but then this whole thing is taken as to the power of -1. So the posterior uncertainty also nicely fulfills this intuition that more data are better. Yeah, so the example is here. Are there questions at this point? Because then the next thing would be to ask why this is the case.
Yes, I have one quick question. Is it somehow consistent across different study designs that Bayesian inference and frequentist inference tell the same story in the end, if you look at the results?
Yes, I would think so. So I have not. So of course, in terms of the results that you get and the whole thing that you do, of course, there's it's always a quantification of signal to noise, right? So t values, p values, posterior uncertainties, and so on. All of them quantify signal to noise. And if there's very little signal, then the signal to noise ratio is very low, and you have a low t value, high p value, and you have high posterior uncertainty, and so on. So yes, I guess one can create scenarios, and this is, of course, if you look into the Bayesian literature, of course, you specifically the early work of let's say the neoclassical, the neo-Bayesian revival, or whatever it was called. You can conceive scenarios where, and we also looked at one example, of course, where you have very little data for the beta binomial, where they tell different stories, at least for the in the case of little data, and so very few data points. And what was the thing? And point estimation. So let's say like this. So if I think one way, so they can, so the way I would see it, of course, one would have to, so you find examples where they tell different stories. And that's then always the case where the Bayesian, so from my experience, that's then where the Bayesian things are more intuitive. However, if you're not in these boundary scenarios, but you have either, so you have a lot of data, and the data says there's very strong signal and very little noise, then Bayes will not say there is no signal, and frequentism will not say there is no signal, and the other way around. So I think the differences, and this is also definitely one thing to take from this, the differences are definitely more in terms of the meaning of things and the understanding of what or the way things are quantified, which are either more straightforward, like credible intervals, or less straightforward, like confidence intervals, but not in the signal to noise summaries that these approaches give. So it's definitely there are differences. Like I mean, this is the whole thing about the maximal likelihood estimator with one trial in the better binomial model. Of course, there are differences, but in the scenarios that, from an applied perspective, people are dealing with, and then it's usually the case that they are not happy with their results. Then it's unlikely because usually there's then not a single data point and things like that, it's unlikely that they will completely tell different stories. I mean, in the end, of course, both of them try to kind of quantify features of the world, of reality, and it would be weird if they would always tell completely different stories. So they tell different stories in specific scenarios, but and then usually Bayes makes more sense because it's theoretically much more coherent than frequentism. But yeah, they don't. It's not, how can one describe it? It's not that I think bees see different parts of the UV spectrum, and to see the world as a bee might be different from seeing the world as a human, that they somehow, yeah, you know what I mean, that they somehow the world looks like that if you look here, and the world looks like that if you look there. Yeah, but I mean, it's an interesting question. You will definitely, if you open more traditional Bayesian or look into the 50s, 60s literature, of course, there will be many cases where they point out that Bayes tells a different story than frequentism. And this is also why sometimes maybe people believe that it will give a different result. But these are, of course, the cases where people try to establish Bayesian inference or inverse probability as a more reasonable alternative to frequentist inference. But in the end, it's signal to noise. So,
okay, thanks. That was very helpful. Thank you.
Sorry for the long monologue. Any other question?
Yeah, I got a practical one. So if one were to use that in a research setting, what would one report in the end? I guess a MUP estimate, and then maybe somehow, as you presented, like the probability of the that the true but unknown parameter is bigger than 0 or something like that.
Yeah, for example. Of course, one can also, if one really wanted this, so I'm basically what I hear specifically on this slide put next to each other is, on the one hand, a Z-test, and on the other hand, this posterior probability. Of course, one could, if one really is into hypothesis testing, one could also use a Bayesian hypothesis test with a I guess Bernoulli prior and then a Gaussian likelihood. So one could make them, if one wanted in an applied setting, an alternative to the Z-test or a T-test. One could make this closer than I did it here. Yes, whatever one thinks is useful. So this whole thing that one has to apply the t-value and the degrees of freedom and the p-value, and if the p-value is smaller than 0.001, one can write that it's smaller than 0.000. All this stuff, this is just annoying. I mean, one should report what one thinks is the useful outcome, if one is interested in that people can use a quantification of uncertainty of one's current study in some meta-analysis. Yeah, it makes sense to report t-values. What I really find ridiculous is this whole thing about anyway, this that isn't there this software that detects whether the t-value and the p-value fit together given the degrees of freedom? I mean, come on. I mean, you just give me a t-value and the number of participants, time in the design, then I can compute the p-value for myself. Anyway, so from a practical perspective, yes, report, for example, the probability that the parameter is larger than 0, if this has meaning for you. or report that the parameter is in a certain interval with very high probability. So here, of course, doing 95% intervals is again somewhat easy. Or is it? Yeah, because it's symmetric around 3.01. So you can, and given the posterior variance, you can say, okay, with 95% probability, after having seen the data and with this prior, we arrive at the conclusion that the parameter is fairly certain in the interval between 2 and 4. And fairly certain meaning 95%. That's what I will report if I had this result. Then I get from a reviewer the comment, this is not how you report this. It's very, we had that with Lilla's paper, and then you get into these discussions what the current APA standard is, and that's just ridiculous. Yeah?
Because that would have been my question, actually, what reviewers kind of also want to see.
Yeah, reviewers are people like you. So they reviewers are, most of the time people are reviewers. You often are people that don't understand what their job is. So first of all, reviewers' job is not to say something is interesting or timely or something like that. Reviewers are people who should read your paper as an external reader and say whether they understand what's going on. And if they have a hard time understanding what's going on, then you might want to improve your communication. But reviewers are not people who should say, no, this should not be published. This should be given to a lower ranked journal or something like that. This is just that everybody does not understand what their task is as a reviewer. That's the problem there. The task as a reviewer is to read it and see, okay, can I understand what's going on? Do I feel confident that I can reproduce based on their data, that I can reproduce their results? That's the task of a reviewer. And what reviewer want to see, that's not the question. The question is, do they understand what's going on? And do they have something meaningful to say? Sorry. But yes, you can also look into the literature and maybe into the psychology, Bayesian statistic literature, what people think one should report. But, and of course, you can, as a reviewer, also think if you can not, so what I, as a reviewer, if I cannot judge the posterior uncertainty of something, then I ask. So if a result is presented as the result is 2, and I don't get from this how certain are you that it's 2, then I might ask, well, can you tell me what's the variability there? How certain are you, so that I can deal with that, and whether that's then communicated using a t-value or using Bayesian inference, I don't mind. Just if people don't quantify their uncertainty, then it's annoying. But how exactly, I mean, t-values are useful for giving signal-to-noise ratios. Okay, other questions? Okay, then let's have as a last bit, have a brief look of why this happens. So where these formulas come from. Actually, this is a special case, of course, of the multivariate Gaussian, and the multivariate Gaussian theory in terms of having a multivariate Gaussian vector and then partitioning this vector and conditioning parts of this vector on the other part of all of this, of which is a special case here, that goes very far. So if you ever have time or whatever, look into I always call them the Gaussian joint distribution, so multivariate joint distribution and conditional distribution theorems, because they are, of course, behind this, although we here take a different approach to show where these formulas are coming from. But they also help you a lot in terms of hierarchical modeling, what people also like, so linear mixed models and so on. So conditioning Gaussians on Gaussians goes a long way, and many things in data analysis. Also Kalman filter, so Bayesian filtering or general filtering, all of this works because of the analytical properties of multivariate Gaussians. And this is here a very special scenario, and we don't ignore this multivariate aspect here, but really one can also, if one establishes and proves the properties of multivariate Gaussian distributions, which are, of course, linear combinations of univariate Gaussian distributions, then one has, like, I don't know, 60% of the even advanced statistical procedures covered. So whenever Gaussian comes in, you have, and of course, you can also nonlinear transform Gaussians, and then you have many more distributions. So that's all behind this. Here we use a little bit of a different approach, namely, again, by looking at the probability density function and seeing what happens. So we go again, starting from this proportionality idea. And do we need a trick then? Usually it's then completing the square something. Yeah, let's see what happens. So we first ignore all proportionality constants, so normalization, and just consider the posterior to be given by the product of the likelihood, which is this product sign times NYI theta sigma square y times the prior and theta mu theta sigma square theta. That's how we formulated our probabilistic model. And then we just substitute the functional forms in there. That's happening in the second row. And then we see that we have exponential terms in there and two constants which don't depend on theta, namely this 1 over square root 2 pi sigma square y and 1 over square root 2 pi sigma square theta. We ignore them. That's why you see in the third row again the proportionality constant. And for the exponential function, we use the fact that if you multiply two exponential functions, that's the same thing as we saw for powers, you can also add their inputs. So this is also where the product sign in the second row then turns into a sum of the arguments of the exponential function in the third row. So this is basically properties of the exponential function, which Bill Lindner can tell you all about because he just taught that. And then there's a little bit of rewriting going on. So you see binomial formula being used in the fourth row for both cases, and then a little bit of rearrangement with the aim of what I can't, so not really, so what was the aim here? So far I can't really tell an aim. So yeah, this, yeah, there's rearrangement going on, but I'm not quite sure what the aim there was, but it goes on. Yeah, so the final aim is to have in the exponential, if you go to the last equation of 24, to have in the exponential a square of theta and theta itself. So you see in the last line of 24, it says exponential of minus 1/2 theta square times things and theta times things. And these times things are then defined here as phi 1 and phi 2 in 25. And then the whole thing that that is just this product of the likelihood and the prior can be written, and that's in 26, as exponential of minus 1, 2 over phi 1 theta square plus 1 over phi 1 theta phi 2. And why all of this? This then refers to this idea of completing the square. So what one wants to do there, what I'm trying to do there is to have in the exponential term something that we know from the Gaussian all along. So you see in 16, there is y minus theta square. So if you have an exponential with a minus sign and then y minus theta square, or something minus something square, that's a normal distribution. That's a Gaussian. Then you have some constants, you multiply the whole thing, but that's the Gaussian feature. And the reason so why theta square and theta were isolated there is that one then can add in 26 in the second row this phi square term. Of course, that means the same as multiplying with another exponential. So again, there's just a proportionality thing happening, but then one gets to, and this is what is in 27, one gets to a form that has a theta minus phi 2 square, which is then Gaussian and everything. So that's just the functional form. It's not properly normalized. It's not a Gaussian distribution, but it has this peak. And one can interpret this phi 1 and phi 2 as the variance and the expectation parameter. And then if we're at 27, we already know again how to normalize this, because this is this Gaussian integral. That's 1 over, so the integral is square root 2 pi phi 1. And to normalize the right-hand side of 27, that's then dividing by 1 over square root 2 pi phi 1. And then we are there, and this whole thing worked because we defined, so then we have in 28, we've seen that, or we see that we now have a Gaussian density with parameters phi 2 and phi 1. And the question was how were phi 2 and phi 1 defined in the first place? And this is what we did here. And this is then where we end up with and have our parameters. So the mathematical trick or the idea here is this completing the square business. And again, it's like we use this proportionality, formulate everything so that we have a function that depends on the parameter of depends on the argument of interest theta, that then looks like a Gaussian. We know how to normalize the Gaussian, and we end up with then the parameter update formulas. I know that might not be that interesting to you, but first of all, I think it's interesting. So you need to listen to know. And the other thing is, it's not that hard. So yeah, one needs to be a little bit familiar with multiplying exponentials. And remembering binomial formulas also not helpful, and doing a little bit of algebra also doesn't hurt, but that's it. So we don't need, I don't know, we don't even need matrix calculus or anything like that. We don't even need calculus at all. We just need algebra. But of course, the hard part, like in the better binomial model here, is of course doing the integration of what you see in 27 on the right-hand side. And this has been solved long time, so we don't need to worry about that. Good. Yeah, so these were the two models that I wanted to discuss. Again, so the main point here is in conjugate models, the prior and the posterior are of the same probability distribution class. And Bayesian inference means taking the data and somehow maybe adding a hyperparameter or dividing by a prior, as a hyper prior parameter, And that's it. So you have these update formulas, and that's Bayesian inference. Again, this is not computationally demanding. I mean, like in the better binomial, we could do this by mental arithmetic. Here, I guess as well. I mean, this is, but of course, I use the computer, but it's not computation demanding or anything like that. It's just adding and dividing a couple of numbers. Good. Any other questions right now? Of course, there are questions that result from looking at these conjugate models. So first of all, what does it mean to have an uninformative prior? So that's this whole objective base stuff that we don't discuss. The other thing is, okay, yeah, this works all out really nicely, but this is just because we assume the Gaussian prior, right? So that's why these formulas work out that nicely, and the same for better binomial. And yes, that it's true. Yes, that's true. But I think in an applied scenario, if one wants to do Bayesian inference, one can, of course, first ask oneself, okay, which probabilistic model do I want to use? And is there a conjugate model for which all the formulas are worked out that I can use that reasonably represents my prior uncertainty and posterior uncertainty? And if there is one, then there's no need to use some toolbox or anything, or MCMC or variation inference, then we can just use it. If one has the feeling or the strong suspicion that that there is not really such a model, then one can, of course, revert to numerical inference or variation inference. And this, of course, leads me to then the afternoon session, which will be on numerical inference. One last thing, because we decided, and I like the idea, that we do it online. I need a little bit more time than until 1. So we start again at 1:30 today, because I need to go home and set up the machine there. Yeah, good. Then, so this was kind of the very basic analytical stuff. And then this afternoon it gets more exciting because it gets to numerics. Good, then see you later.